Okay. Hello to everybody. Of course, it's a great honor for me to receive this medal. So thanks a lot to the award committee. So the title of my talk is 40 Years of Speech and Language Processing, from Bayes decision rule to deep learning. And so I'm going to share my experience, my interpretation of what happened in the last 40 years in the area of speech recognition and also a little bit of language processing. Some of my views might be controversial, we will see. The community has come up with a large number of concepts for models and also training criteria. And the question is, where is a unifying concept? I mean, the criterion of science is to have a few principles, guidelines that can be used really to describe the whole area. And my answer to that question, the single guideline, if I'm forced to select a single guideline, a single framework, then my answer is this is statistical decision theory and Bayes decision rule. And what about deep learning? Yes, deep learning has been very successful, but in my view, it's only one of many methods that are available in the area of statistical modeling. Very, very successful, yes, but we have to remember there has been life before deep learning, and there will be life beyond deep learning and after deep learning. Okay, so I'm going to talk about speech recognition, machine translation. Machine translation is really a purely symbolic task. We go from a sequence of symbols in the source language to a sequence of symbols in the target language. The relations between input and output symbols do not have to be monotonic. This is different from speech recognition, where we really have a strict monotonic relationship between input sequence and output sequence. And this is also the case for handwriting recognition. I mean, this is not really a one-dimensional input, it's a two-dimensional arrangement. But by considering the image to be a sequence of vertical slots, this can be interpreted as a one-dimensional input sequence. And so the same methods as in speech recognition can be applied. So my experience is really based on a couple of large-scale projects that I've done over the last nearly 40 years. So the first one I would like to mention is speakers. At that time, large vocabulary was 1,000 words. It was speaker dependent. Then we have the Verbmobile project, which was already speech translation, 8,000 words. Then TC Star, in which we worked on speeches given in the European Parliament. It was speech translation. Now, in order to make the MT part robust with respect to speech recognition errors, we use data-driven methods. That was also already the case also in the Verbmobile project, but this was really artificial data. I mean, the data here, they were collected by researchers, for researchers in the research lab. The data did not really exist outside science. But here, speeches in the European Parliament, they exist independent of any scientific activity. So this is really real life. And in my view, this was really the first research prototype for speech recognition, for speech translation, on unlimited domain and real-life data. And it was fully automatic, it was not real-time, and at that time it was done without deep learning. Then here we worked on basically European, let's say Spanish-English. Then there was in parallel, there was a project Gale, in which we worked on Chinese and Arabic. There was a follow-up project Bold, and then I also would like to mention the project Quero, funded by the French government, in which we worked on a couple of European languages, TED lectures, speaking style was more colloquial speech, and also handwriting recognition. In my talk, I'm going to refer to a couple of mathematical models, equations. So I think it's a good chance now first to present the operational systems we had at that time. Let's see whether that works. No? No, sorry. It's the wrong one. This should be Spanish. Yes.
En cuanto a la premisa de partida,
okay.
La premisa de partida es que el fenómeno de la inmigración es un fenómeno actual y creciente.
No, it does not.
Y que no va a parar por mucha voluntad de poner barreras o...
You cannot hear it. Ah, sorry, we forgot the audio. Yes. I hope now it's going to work. It's the most important thing.
de poner muros en el mar que algunos tengan. A partir de aquí, de lo que se trata, como también se ha dicho, es de regular estos en cuanto a la premisa de partida. Y la premisa de partida es que el fenómeno de la inmigración es un fenómeno actual y creciente, y que no va a parar por mucha voluntad de poner barreras o de poner muros.
So that was 15 years ago, recognition for Spanish and the translation into English. And at that time already the topic was immigration.
En el mar que algunos tengan. A partir de aquí, de lo que se trata, como también se ha dicho, es de regular estos flujos. De regular esos flujos migratorios, pero de regularlos.
Then we also worked on Arabic.
قالت وكالة أنباء فارس الإيرانية شبه الرسمية إن 3 انفجارات وقعت اليوم في جنوب البلاد، لأنه لم ترد أنباء بشأن سقوط قتلى أو جرحى. وأضافت الوكالة أن الانفجارات
Does not work.
各位好，欢迎收看这一时段的中国新闻。第6轮6方会谈第2阶段会议将从今天开始在北京举行。目前，各方代表团的团长已经陆续抵达北京。
So these are systems, operational research systems that we had 15 years ago. So that was a long time before there was Siri, Alexa, Google Assistants, that's what all the products are called. Then I should also mention the French project. Let's see, Hermann on happiness. I skipped the music.
Talks about happiness these days. I had somebody count the number of books with happiness in the title published in the last 5 years, and they gave up after about 40, and there were many more. There is a huge wave of interest in happiness among researchers. There is a lot of happiness coaching. Everybody would like to make people...
Okay, I think that should be enough. So now let's come back to my slides. I think, in my view, interesting research work on speech recognition started in the 70s. And the idea was, okay, we have a couple of knowledge sources. Then we have to recognize phonemes. But of course, the problem is phonemes could not be recognized reliably. We don't know, even today, we don't know the phoneme boundaries. They are difficult to find. The same with word boundaries. Then also the structure of the sentence should be taken into account. It should be well formed from a syntactic semantic point of view. So we have interactions between all these levels and ambiguities. And the approach advocated by Jim Baker in his thesis at CMU, PhD thesis, and advocated also by Fred Jelinek in his team at IBM, was to say, okay, we have to do probabilistic modeling and use Bayes' decision rule. So let's look at the details. We are given as input a sequence of acoustic vectors after spectral analysis, and then we want to generate a word string. So we consider the joint generative model, which is decomposed into a language model and acoustic or acoustic phonetic model. Now, the language model at that time was typically a word trigram model, statistical word trigram model, and the advantage of this decomposition is the language model can be learned from text only. This is something I'm going to come back to later on when we're going to talk about end-to-end systems. For the acoustic phonetic model, annotated data are needed, and in those days it was the most successful approaches were generative in Markov models with, let's say, discrete modeling, like after vector quantization, Gaussian models, Gaussian mixtures, and a lot of other refinements. So these models had a nice mathematical structure. There were sort of closed form solutions for training within the M algorithm. And at that time, it was sort of efficient because, of course, computation time computation power was not big at that time. But from a machine learning point of view, this was really not perfect, because learning such a distribution over continuous valued vectors is really difficult. And that changed over time, as we will see. And then we have the Bayes decision rule in order to generate the output. So a typical picture that was used also by the IBM team, and that also used for my own systems was, okay, we have an acoustic model, we generate a sequence of acoustic vectors, we have knowledge sources in terms of phony models, pronunciation lexicon, and a language model. These probabilities are combined, and then we have to find the string with the highest probability. Now, finding this string with the highest probability was computationally expensive, so IBM built a system that used isolated word input, so you had to make clear pauses between the words. But there was an operational system in 85. It was speaker dependent, about 5,000 words. And I remember that Bob Mercer gave a demonstration of the system to me, system run on a big mainframe computer. And he demonstrated that the system could resolve homophones. He used the example 2. 22 people are too many to be put in this room. So this was isolated words, but all the concepts were, or many of the concepts were in place already at that time. So, of course, the vocabulary size increased over time, also the speaking style. But then in around 85 or so, there was, people came up with the criticism that these systems had a lot of parameters, and there was a saturation effect, the accuracy did not improve anymore, and instead, some people advocated we should do a rule-based approach, we should put explicit acoustic phonetic knowledge into our system in the form of an expert system. This was never really successful. I think in the end the problem is really the coverage. You have a good coverage, sufficient coverage, and of rules, and also the consistency of rules might pose problems. At the same time, important methodology was developed by the community. Namely, the community sort of agreed on standard data, training and test data, so that the results of systems could be compared against each other, like a resource management task with 1,000 words, Wall Street Journal 5,000 words and 20K, and schließlich North American business news using vocabularies of 64K and larger. And in addition to that, there was also switchboard, which is telephone conversations. And then NIST, DARPA, they started about the same time with their comparative evaluations. And then virtually all, let's say, high-performance systems at that time were based on generative and Markov models and some refinements. There was one system that was really different for Wall Street Journal evaluations, a system built by Tony Robinson, in which he used a hybrid HMM with recurrent neural networks. And then in 2009, there was an ICTA evaluation on handwriting recognition. In this evaluation, Alex Graves could produce the best results using his CTC approach. And then around 2011 or so, deep learning and so on became mainstream. So let's look at the hidden Markov model. We are given the sequence of acoustic vectors as input. We want to generate a word sequence, which is represented as a sequence of labels, phonetic labels, letters, card labels. And this sequence is either given in training in form of a transcription, or we want to generate during the recognition process. And now the generative version of the HMM says, okay, we are going to model this probability over this sequence of acoustic vectors by the structure with first order dependencies. So we sum over all possible paths in this trellis. And along each path, we look at the contributions from transition probabilities and emission or observation probabilities. And as opposed to that, it was Hervé Bollard and Christian Wellekens who suggested instead you could really use directly the so-called label posterior probability or glass posterior probability. So given this sequence and given the knowledge and given, let's say, a time frame at t, what is the probability of seeing any of these possible card labels? At that time, let's say 5,000, 10,000 or so, and later on we are going to continue with CTC, then it will be just 40 monophone labels or 40 letters or whatever. And from a machine learning point of view, this is much easier to do than this one. So the result then is a probability of the output sequence, posterior probability. But mathematics is much more complicated. And in machine learning, I think this fact had been very well known, but people thought, this is speech, we have to handle sequences, somehow we have the EM algorithms, and somehow life is different here. It was then also Bollard and Willekens pointed out, okay, the output of a neural network can be interpreted as class posterior or class posterior estimates. Along the same line, John Bridle showed that when we compute the posterior distribution of a joint model consisting of a class prior and a Gaussian model, then we get the softmax, assuming class-independent covariance matrices. So that means the operation of a multi-layer perceptron for single vector input and softmax output layer can be interpreted as follows. These layers here, they perform feature extraction independent of any class index, and then finally here we have the softmax where the class index plays a role. So you could say all these things were known already 30 years ago. What is different now after 30 years? My view is basically we have learned how to handle or how to better handle a complex mathematical optimization problem. At that time, 30 years ago, we didn't have powerful computer hardware. We didn't have experience with numerical optimization. Meanwhile, there are lots of recipes on how to carry out a backpropagation and so on. And as a result of this, we are able to handle more complex structures so that we can have 10 or more layers. And as I said, Tony Robinson was quite successful with an RNN. Now, RNN typically in the simplest case has just one hidden layer, but when you unfold it over the time axis, then you really see when you compute output at time t, there are a couple of hidden layers that contribute to this output. So this was already hidden, a deep structure, well, nearly 30 years ago. Now let's move on to CTC. In my view, CTC is a kind of a special hybrid model, hybrid HMM, where the outputs are now just letters or monophone labels rather than 5,000, 10,000, 20,000 card labels. And we have constraints on the possible labels. Depending on the transition, only certain types of labels are allowed, because there is an additional set of labels, or one label that is referred to as a blank label or empty label, or don't care, you might call it, which also stands for silence portions in the signal and can indicate repetition of true labels. So either you can compute the sum over all paths, as we do in generative hybrid hidden Markov models, or you can compute a single best path. In addition to that, there are no transition probabilities. So finally, the posterior probability can be computed like this, where for the normalization also the special symbol epsilon has to be included. Now, when you carry out a mathematical analysis or also experiments, you will see that the optimum solution in terms of the best path tends to have a path that produces a maximum number of epsilons, and the true labels will show up only once. And you can use this as a constraint in an extension of these models, which is referred to as RTN Transducer. We then say, okay, when we have a forward transition here, or a vertical transition in the trellis, then this can be a true label, whereas all the loops, they need the label epsilon, which means the horizontal transitions here in the trellis have an epsilon. I will skip other details. So in this slide, I've tried to summarize what happened, let's say, between neural network modeling and acoustic modeling. I think the first one who worked on using neural networks for speech recognition was Alex Weibel and his colleagues. They used time delay neural networks, and they used a structure that is nowadays known as convolutional networks. So it was a couple of years before they were introduced in image processing by Yann Lequin. I mentioned John Bridle with the softmax. I mentioned the hybrid HMM interpretation of ANN outputs. Then here there are two papers that sort of anticipated what is nowadays known as sequence discriminative training. But all this work did not really, let's say, produce operational research systems that could produce competitive results on Wall Street Journal tasks or similar tasks in these DARPA evaluations. But there's one exception, and that is really the system by Tony Robinson. An RNN neural network was used in the context of a hybrid HMM, and this was really operational research system. Then in contrast to this hybrid concept, there is a concept that is referred to as, was, and maybe still is, a concept that is referred to as tandem HMM. That means we use a neural network for feature extraction, and this is followed by a Gaussian model. By a Gaussian HMM, sorry. And I mentioned already Alex Graves' results for CTC on handwriting recognition in 2009, and then around 2011, the deep learning became mainstream. So let's just say, want to say a few words about this difference between tandem and hybrid approach. So we were able to get a 22% word error reduction on the Quero task, for which I showed the demo in the beginning. This was actually at Interspeech 10 years ago in Florence, and in the same session there was a paper by Microsoft using a hybrid approach on switchboard, public database, and they could report improvements by 30%. I mean, we had some work on the comparison between tandem approach and hybrid approach. You could show that they are equivalent, but in the end, the hybrid approach is more elegant and more compact, so it's widely used nowadays. I skip that one. So we have seen different types of structures in order to model probability distributions. The goal, of course, is here to capture the inherent dependencies in the strings, output string, input string, and across the strings, using some task-specific knowledge about speech and language. And in my view, this is really a task that is comparable to physics or other natural sciences. We have to take nature as it is. Speech and language, they existed a long time before we had computer scientists, phoneticians, linguists, mathematicians, statisticians. And the goal is to capture the dependencies that exist in the world of speech and language, and then we have to build models based on this type of knowledge. And there's also a large set of grading criteria. I have not talked about them yet. So the question is, how can we organize this maybe chaotic set of training criteria? What is unifying concept? And the answer, in my view, is really Bayes' decision rule and statistical decision theory. You find these things already in textbooks in the 70s or even before. At that time, people didn't know, were not aware that these things were going, that these concepts were going to work so well for ASR and also general string processing. So I just would like to summarize this concept from a very mathematical point of view. I do not care about implementations. We just imagine we have a really huge database, really huge, in terms of input-output strings. So are these pairs? Okay, R is the index for each pair that we have. And then from this, at least conceptually, we can compute the empirical distribution. Now this is a relation because we have pairs. And now we want to convert this into a guessing game. Knowing X, we want to predict C. Now, because now this is a function, we have to make errors because we want to convert a relation to a function. So we have to measure errors. So we have to introduce a loss function. When we look at the string as a whole, it's a 0-1 loss. When we look at the individual symbols, like deletion errors, substitution errors, and insertion errors in speech recognition, then it's edit distance, word error rate, and you can also extend this for translation error rate by including swap counts. Then the question is, given this loss function, what is the best answer I can generate? And for this input X, and the solution is given by what is known as Bayes' decision rule. We average the cost over all possible output strings using this posterior distribution. And then we have to select the output string for which this average cost or expected loss is a minimum. Now, this is completely independent of any parameters, of any model. This is just a mathematical concept. But there is no generalization to new data because we can only talk about the data that are in our database. Now the next step is to say, okay, we want to replace our empirical distribution by a model so that we can handle unseen data with a model that has maybe a huge set of free parameters. And then we put this into our decision rule, which strictly speaking is not the true Bayes decision rule anymore, but pseudo-Bayes, but nobody calls it that way. From a mathematical point of view, the true Bayes decision rule, you have to use the true distribution of the data. Then there is a simplification. For the 0-1 loss, this can be simplified like this. And this is the rules that is often found in textbooks and also used in 95% of the publications. So there are two questions that come up. How much do we lose when we make this simplification? So to what degree does the exact form of the loss function matter? And what are suitable training criteria for our model? Because so far we didn't say anything about how to train this model. Now, there's a simple answer to the loss function. We worked on this a couple of years ago, and we found out that if the loss function is metric, which is a metric, it satisfies the triangle inequality, which is the case for word error rate, edit distance, and if the string with maximum probability has a probability larger than 0.5, then the two rules must produce the same result. That can be shown just mathematically. So there's a complete equivalence. So you can expect a difference only when you talk about the region experiments with high error rates. So for example, we worked on that problem and we worked hard. Then we were able to reduce the error rate, let's say, from 41% to 40%. But you can see this difference only when the error rates are really high. There are further refinements, which I'm going to skip. Now the more important question is about the training criteria. Of course, the idea is that our model should somehow approximate the true distribution. But the question is, how do we measure this approximation? And an even more important question is, we are not really interested in this approximation. We are interested in minimum classification error, in optimum performance. And for that, we carried out some mathematical analysis. In 2003, this is a paper I think that nearly nobody has read, so I want to make some advertisement for it. So we strictly have to distinguish between the error rate for the true-based decision rule and for the model-based decision rule or the pseudo-based rule. So we have these two rules, the true distribution and the model, and then you can show that the squared difference of these two error rates can be upper bounded by this term, and this is exactly Kullback-Leibler divergence. And when this empirical distribution is based on our pairs of training data. So when you look at this term, then this term is independent of any model, is the data, it's independent of any parameter. So what is left is just our model. And this is really identical, this criterion minimizing the upper bound is identical to the cross-entropy training criterion. So when I put everything together, this is the picture that I want to use. We have to agree when we want to perform a task in natural language processing, speech recognition, what is our performance measure? Then based on that, we have a decision rule. We do not know the true distribution, so we have to define a model. The model has 3 parameters that we have to learn. We have to learn them in such a way that somehow the performance is taken into account. So this should result in the definition of the training criterion, for example, like cross-entropy. But then cross-entropy still requires numerical optimization, backpropagation, or some other gradient method for optimization. So we do this using training data. We have the parameter estimates. We put this in our decision rule. And then we are facing a search problem, generation problem, combinatorial optimization problem, because we have to find the string either with the largest probability or with minimum average cost. So I talked about performance measures, probabilistic models, training criterion. I did not really talk about this generation procedure. And I think models over time have improved so much that this is not that much important anymore as it was 30, 40 years ago. At that time, the models were not really very powerful. And at that time, efficient decoding procedures, search procedures were very important. And my team and also other teams have worked a lot on this problem. But to be fair, nowadays, it's not so important anymore. So now let's look at the model as a whole. So the analysis that I showed suggests that the posterior probability, the output posterior probability, is a key quantity. And we are going to model it like this. We say, okay, we are going to have a language model, and we are going to have a acoustic model, and we are going to combine them in this exponential way or log linear way. So we have exponents here, and we do renormalization. This is really an imitation of the generative approach, where you can do this separation in a natural way. Here it's a little bit artificial. But this one has the advantage, okay, we can separate the language model, but here we have a generative model which is really difficult to learn from a machine learning point of view. Instead, we are using a posterior probability because it's maybe mathematically more difficult to handle, but it's easier from a learning point of view. And we have the renormalization. And of course, as I said before, the language model can be learned on text data, and can be learned from text data. And the acoustic model is one of these finite state models, as I call them, that I've mentioned, using here a frame label posterior distribution, which is the key quantity in the full model. So now let's look at the criterion. The analysis that I suggested, that I presented, suggests that we should really use this cross-entropy training criterion at the level of the output strings. The distribution over the output strings is defined like this: language model, acoustic model, renormalization. Now this is really a difficult optimization problem. And the first time I think I saw it in the speech context was in a paper by IBM, Lalit Bal. They called it MMI, Maximum Mutual Information Criterion. Nowadays people refer to this in the neural network community or in the machine learning context as sequence discriminative training. This is difficult, as I said, so first approximation you might just ignore the renormalization by the denominator. So we have this language model and the acoustic model. Applying the logarithm to the product means the optimization problem is decomposed, and we can train the acoustic model independent of the language model. And you can either do full sum training, best path training, and I do not have time to show that. When we talk about these neural, or let's say hybrid finite state models or neural finite state models, you can show that the EM algorithm still works. It's more complicated, it's different from the classical one, but the concept still works. Now, of course, a better approximation is somehow to take this denominator into account. The problem is we have to carry out a sum over many astronomically large number of word strings. So we might use a word hypothesis lattice to limit the number of terms in the sum, or as suggested by Dan Povey, we also might use a simplified language model with sort of recombination dynamic programming, in which this sum can be carried out exactly for a simplified language model. Now all these things, they apply to the string error as the criterion. When we now move on to symbol errors, word errors, then things get even more complicated, and people talk about minimum base risk, minimum word error rate, state level minimum base risk, and so on. Now in this context, I think it's interesting to ask the question, what about this end-to-end concepts that we have in pure, what I call, let's say, pure neural network approaches? First question from my side is, what does end-to-end mean? Do we mean the training criterion, a single global criterion for optimum performance, independent of the model structure, or do we mean that the model has a monolithic structure, which is, let's say, easy and elegant from the programming point of view, but the question is, my critical remark is it adequate to the problem? Because in typical tasks in research and even applications in speech recognition, we have, let's say, it's easy to get 100 million words or more for the language model from the internet, from archives, from electronic books, and so on. Whereas for the transcribed audio, we are happy if we have 500 hours. 500 hours amount to 5 million words as opposed to 100 million words. So we do not do a good job if we ignore these 100 million words. So my answer to this end-to-end concept is, yes, we should do it surely if training criterion is concerned, because we want to have a system with optimum performance. When we talk about the model structure, then the critical question is, can this model structure really reflect the specific situation of the training data? So now, how much more time do I have? Any time or what? 10 minutes. Maybe I need some more minutes. Okay. So here I show some results that we got for the Quero task that I showed in the beginning. For the hybrid HMM with Gaussian mixtures and sequence discriminative training, here are the error rates. And here we have neural network approaches, hybrid models. feed-forward multilayer perceptron, LSTM, RNN, and we see that this error rate can be reduced from 19.2 to 8.2. I mean, the best one we could get without neural networks was 19.2, so down to 8.2. So this is really an improvement by 60% relatively, of course, which is quite impressive result for deep learning. And here also are using a neural network-based language model. I'm going to talk about that in a minute. So also we worked on Switchboard because it's a public database where we can compare our results with what other teams report. So we have, again, hybrid HMM here, no adaptation and speaker adaptation, yes. Baseline approach, then sequence discriminative training, special variant of state level minimum base risk, and a neural network language model. Then we see, when we look at traditional, this is Switchboard and call home. When we look at the average error rate, we see it goes down, and there is an improvement typically by 1% or so absolute when we use the adaptation method. And these numbers compare quite well with what other teams report. This is 300 hours of training. When you move to 2,000 hours, then of course the error rate goes down. And here are some results concerning the comparison between HMM and attention modeling for the LibreSpeech task. So here we have the attention modeling. Traditionally, there is a first part of the data, test data, development data, that is called clean, and the second part that is called other, noisy or whatever. And here you have all these specific results, and you see we get improvements when we include a language model, and a special language model, transformer language, will give additional improvements. And similar results for the hybrid HMM, where we have in between here sequence discriminative training. And again, these numbers compare favorably well with what other teams have reported at that time, 2019. Maybe a word about the attention mechanism. I do not have time to look at it in more detail. I mean, when we use these hybrid HMMs, finite state models, we basically carry out a sum over all paths, and for each path we have the probability distribution. So we basically sum over probability distributions. When we look at the attention mechanism, it does a factorization of the conditional probability right away, and then we introduce the attention mechanism, which means we compute an average representation of these input representations with weights that depend on the output that we have generated so far. So the difference is really the averaging or summing here is over the distributions, and here it is over the internal representations that are computed for the input before we really start the synchronization mechanism. Skip that. Now a few words about language modeling. Now, of course, you can use count. The traditional way until 5, 6, 7 years ago was to use count models for the language model, 5 gram, 4 gram, whatever. You can also use the full history when you use RNNs, or you can truncate the history. Then I'm talking about the K-gram MLP. So we did this here for the 10 gram. So we see we are getting clear improvements by moving from count model to a feed-forward MLP, RNN, and LSTM again gives improvements, and even more improvements when we use 2 hidden layers. Now you can say this is perplexity. What we are really interested in is word error rate. So we built an interpolated model, because when we did the experiment a long time ago, 5 years ago maybe, the computing power was difficult to have. So we had only a small number to train the number of data to train the amount of data to train the ANN model. And here you have the resulting perplexities and the associated word error rates. So we have a 30% reduction in perplexity and a 15% relative reduction in the word error rate. So when you plot these results, this is what you get. This is logarithmic scaling, and this is sort of linear of straight line. And because this is logarithmic scaling, this can be expressed as such a power law. Word error rate is proportional to a power of perplexity, where the exponent typically is a range 0.3, 0.5. And first time this was formulated, as far as I know, was by John McCool and Richard Schwartz. Now this is a small range of perplexity, so we built also models with higher perplexities, and again we see a straight line now for a range of word error rates from 11 to 31. So I think it's a scientific challenge to find a good theoretical justification for this law. Now, before I end, I want to say a few words about machine translation. I guess there are many young colleagues here in the audience that are not aware of the fact that the use of statistical methods in language processing written text, was quite controversial. And this really goes back to Chomsky. He didn't like at all the idea of having probability statistics in linguistic processing, in processing text. And one of the statements he had is the notion of probability of a sentence is an entirely useless one under any known interpretation of this term. And he was quite successful with his work on formal grammars, so he was an authority, and many people thought he's right with his statement. So the mainstream approach to MT was really rule-based until around 2000. IBM, around 1989, started a project in which they tried the statistical approach to MT. This was more or less successful, competitive with rule-based or conventional systems. Then, at the end of the project, people, Bob Mercer and Peter Brown, they left and joined the hedge fund Renaissance Technologies. When I started at the university, I took up the work they had done, and we extended it along various dimensions. We introduced log linear modeling for translation. We introduced a phrase-based approach where instead of single words, we are looking at word groups, so-called phrases. And then in 2004, one of my first students on this topic, Franz Och, he joined Google, and he attracted more of my PhD students. And they started the service Google Translate using the phrase-based approach in 2008. And then around 2004 and later, this data-driven approach became mainstream. This was still based on counts. And then in 2015, Benjo's team, they introduced the attention mechanism using neural networks, which was even more powerful. Now, what we have doing in addition to the attention model, we are doing a neural HMM, where we consider mappings from the target positions to the source positions. You can really reformulate everything like in speech recognition. So you have a trellis in which you have to sum over all possible alignments. You can use a framework of the EM algorithm and so on. And here we have some results. If you're comparing it with the attention mechanism, this was the original LSTM RNN-based attention mechanism, and self-attention transformer, as it was introduced by Google, which is still the best approach to machine translation nowadays. And we see that this neural HMM, this is competitive maybe with the attention model, but not quite competitive with the transformer model. But still, maybe there's room for improvement. But it shows that there is some life beyond just the attention models, also in translation. So I think I should come to an end. So I tried to present my unifying view of what base decision theory and the statistical approach has to offer. Deep learning really is very powerful, very good, but it defines only one family of probabilistic models. In the end, it's just matrix vector product and nonlinearities, and maybe there are some structures beyond that. What I find also very remarkable and very surprising is the success of deep learning for symbolic tasks. Like in language modeling, neural networks are quite successful, MT, and also other NLP tasks. So this is, I think, really something remarkable, because you can get extremely good performance using these data-driven neural network concepts as opposed to rule-based approaches. But as I said, deep learning is one statistical method, and there was life and will be life outside deep learning. So it's the picture that I tried to explain. Now, if you ask me where do I see challenges, then I think it would be helpful if we could have a better theoretical framework for the types of neural networks that we are using, in particular also a theoretical framework for the practical aspects of backpropagation gradient search. Then I think in terms of ASR challenges, we will work on more difficult tasks like meetings, colloquial speech. We need more robust systems. Maybe unsupervised training is going to help, where we do not need labeled data. Then I did not mention this. Also, we can replace the spectral analysis, Fourier transform, or whatever we do by a neural network approach. We did this in 2014, and meanwhile, I think there are quite impressive results reported by the Facebook team. And then in that context, also I would like to mention speech translation, with which I started. But the challenge then, I think, is really to come up with an architecture that is able to exploit the three types of training data that we are having. We are having a fair amount of data for ASR in the source language. We're having a huge amount of data for text MT at the text level, and we have a small amount of data for this direct path, which means we go from the speech signal in the source language directly to the text in the target language. So I think the challenge is to find an architecture that is really able to benefit from all three types of training data. And I think that's the right time to stop.
Hermann, thank you very much. Okay, so we have time for some questions. I know that Mark Ailes is actually not online, so he is. Hey, Mark's there. All right, there he is. I was told when we started that you weren't online, but now you are. That's good. So, Mark, if you would monitor maybe any questions that might be coming from our online audience, and I'll look to see if there's any hands up for questions here. First one.
Thank you for this very interesting talk. And in the last figure that you set up, I would like to add one more box. Maybe you could use it, like to have speech in the target language. And
so you're talking about this figure?
Yes. The last one that you showed.
Oh, sorry. This is an error. It's embarrassing. This should be speech. Sorry. Of course, this should be speech. Sorry for that. Nobody maybe paid attention to that. Of course, this should be speech. I think you're the first one. I've been using this for a couple of talks. Your first time to pointing this out. Thank you very much. This is embarrassing, I must admit, but okay.
Mark, do you have any questions online?
Yes, can you hear me?
Yeah.
Excellent. So it's a question about language model complexity, and it really comes down to the fact that as you change the vocabulary, for example, swapping from words to subword units, it's very hard to compare them. Can you actually make a comment about being able to compare perplexities when looking at subword word part models, for example, and whole word models in terms of the ability to predict word error rate performance?
I'm not sure whether I understood your question. Question about subword units in the context of language modeling?
Yep, and the ability, whether you can actually make any inference when comparing subword units for language modeling and whole word units for language models in terms of complexity.
I mean, the results I presented were done. Sorry, the results I presented were done using full word forms. I think there are people that report also good results with using BPE byte pair encoding units. I mean, you can convert, if you do it correctly and carefully, you can convert perplexities from the word level to perplexities to any type of subword units that you are using. So I think in the end, it will be a question for which system you get all the details right, as I'm saying, and get better performance. But I do not see, I mean, the only attraction of these subword units, in my view, could be that you are not limited to a closed vocabulary. But this is maybe a theoretical aspect. Maybe, I don't know.
So I should have answered. That was a question from Askas and Salim Bayeves. Sorry, my apologies for the pronunciation. So I should have said that at the beginning. John, do you have a question in the room?
Question in the room? I could ask a quick question. So when we looked originally at early speech recognition, the tasks were a little bit more text dependent or smaller vocabulary, or you were talking specifically to a machine, a human-machine interaction. So the speech tended to be a little bit more directed and not so random. Today, there's much more emphasis on naturalistic audio, talking to smart speakers and IoT applications and so forth. So when you look at the traditional approaches that you've pioneered, 10, 20, 30 years ago versus some of the machine learning techniques today, where do you see the biggest challenges in going towards more fully naturalistic conversational interaction and trying to do speech recognition on that? And what are the implications of trying to do that type of work for machine translation? Because now it's more difficult.
No, I think that's a lot of challenges that you've brought up. I mean, the models that we're using nowadays are really not, the concepts are not that much different from the models that we used 30 years ago when you said, or 40 years ago, the people really explicitly talk to a machine very carefully with very good articulation. So the models from that point of view have not changed, apart from the fact that we're using neural networks nowadays. So I think, I don't know, I think we need ideas in order really to incorporate, let's say, general structures in our model, like if somebody speaks, has a certain dialect or certain accented pronunciation, I should call it, then this will be true for all the speech he or she is producing. But right now, our models do not take this into account. I mean, to a certain degree, when you have some speaker adaptation, that does it, but it's not really, in my view, the ultimate solution. So I think, I mean, of course, you can try to cover to counteract these problems with more and more data. Yes, that's one way, but the other way, a scientific challenge is to come up with better models, for which I do not have an answer, but maybe somebody has. I don't know.
Other questions from the audience? Hansa.
Thank you very much for your talk, Hermann. I have one question about the structured knowledge versus data. I've asked this question a couple of times. So there is lots of efforts people have spent on creating word nets or ontologies or maybe some classification of animals, but basically whatever that resembles graphs. And there are other people that say, well, you can throw all this away. All we need is raw text and raw audio data, and we'll do the best recognizers on that. What's your opinion on using this structured knowledge in nowadays machine learning?
I think, again, it depends on your data situation. If you have a really huge amount of data, maybe you can do a good job without these structured knowledge formulations or databases. But if you have a new application, new task, if you want to have a product, then maybe in the beginning you have only a small amount of data, and then maybe these structured knowledge databases are helpful. So I think it's really a question of the amount of data. If you have enough data, you can hope, I'm not sure, you can hope that you do not need these things, but if you start with a small amount of data, then I think such types of structured information, structured knowledge sources might be helpful. I mean, we also typically use a pronunciation lexicon. Some people try to get away from that. They do want to do recognition without an explicit pronunciation lexicon. Again, I think it's a question of the data. If you have enough data, and if it's not English, is maybe very difficult in terms of the pronunciation lexicon. If you look at other languages, then maybe you can do it's easy maybe to do without a pronunciation lexicon if you have enough training data.
Sure.
John, I have a question from the chat, if we've got time.
Go ahead.
Okay, in fact, I've got a series of questions. So, Hermann, the first question is from Hardik Saylor. Again, it's a subword unit one. Subword units like BPE for ASR tasks are based on text data only, without any acoustic knowledge. What are your views on this? Should we be incorporating more acoustic knowledge when trying to get subword units such as BPE?
I mean, we are using these BPEs also for attention modeling, yes. But I don't know. I tend to agree. I would expect I would expect, but maybe I'm wrong, that we should be able to do a better job if we take into account the acoustic data when deciding what the subword units should be. But I'm not sure whether anybody has done work along these lines using the neural network approaches. I mean, 20 years ago, 30 years ago, of course, people tried to have a look at these things, what are suitable subword units and so on, and they came up with CART and all these things. So
okay, can I? Oops, sorry, I've got quite a few questions coming through on the chat. If we've got time, and there's no. Have we got time for a few more questions?
No, I think we got to stop. We got one more question in the audience here.
Thank you, Hermann, for this presentation. You said if you have more and more data, you can probably learn everything. But do you think there's a limit because the models are getting bigger and bigger and bigger and bigger? That makes no sense that they actually get bigger. Is there a limit to model growth?
I mean, that's a question what you're talking about. Are we talking about basic science, independent of any applications? Are we talking about practical applications in the near future? So, I mean, if you really say I'm only interested in basic science, then yes, you could say I do not look at this data game. I work with a small amount of data and try the best I can do. If you want to build an operational system for a product or close to a product, then your answer might be, okay, I'm trying to get as much data as I can. So, I mean, that's all I can say.
There should also be some latency constraints, right? So from an operational point, you also want to have some latency requirements.
I do not get it. Privacy, latency?
Latency. He's asking for a latency constraint.
Latency? In what sense? Are you talking about speech translation or what? I'm sorry, I'm confused. Latency? I don't understand. What is latency here? But time delay for what? For recognition or for research or what?
The amount of time it takes to process it.
You mean just the computation time, just practical computation? Yeah, but I think then I trust to my colleagues in computer science. They are going to come up with more powerful hardware in the future. And
So Hermann, I think we want to try to draw this session to a close. I want to ask one statement, and I'm kind of hoping you're going to give me the right answer. Hermansky.
So you know the answer already.
Yeah. So Hermansky started off our session here. He cited Noam Chomsky for some of the early work in linguistics. Looking at your career in speech recognition, speech translation, machine translation, we've got many, many students in here and also online. Should they go back and read papers older than 5 years, or has everything been invented the last 5 years?
No. I mean, I try to show that, of course, there has been very important scientific results 40, 50 years ago and more, and even before that. And of course, knowing something does not hurt. The question is, what are you going to do with your knowledge? Okay.
Well, let's thank our keynote speaker, Hermann Ney, for his wonderful talk. Thank you very much.